Hello and welcome to the online version of the Calculus Bootcamp for the Business Calculus and Algebra course. To be included in this presentation are some helpful foundational knowledge that you may need a little refresher on, keywords that you will come across in the business applications questions that relate specifically to calculus concepts, the basic derivative rules that you'll need, the ones that you're going to see and need to use in class, and some tips and tricks that may be helpful. The first question you might ask is, what is a derivative? And if you've had no experience with calculus in the past, that's a very valid question. So mathematically speaking, the derivative of a function represents the slope of the tangent line at a point on the graph. But what does that mean within the context of its business applications? How is a derivative helpful? Well, the derivative allows us to determine not just a value at a point in time, but how much that value is changing at that point in time. And this information can be invaluable in a business setting to see trends and to make business decisions based on the trends that are observed. Some key words that you'll see in our business applications questions, of course, are slope, which is the mathematical kind of definition of a derivative, rate of change, so again, how much something is changing at a specific point in time, marginal, so you'll recall from when we were looking at algebra questions, marginal meant how something changes with one more additional unit. So we could have marginal profit, marginal revenue, marginal cost, and so on. Depreciation was a specific concept that we saw earlier with our algebra questions, and now we're going to apply calculus concepts to them. So depreciation is how much something goes down in value year over year. Growth rate, of course, how much something grows. Something can grow exponentially, such as an investment in a compound interest investment vehicle, or if we look at the social sciences, health sciences, viruses, and so on, can grow, have a growth rate, and we can view how quickly something is growing by looking at the derivative. Energy consumption, age distribution, and producers and consumers surplus are all business applications which will involve derivatives and integrals. So we'll get to that later in the semester. Before we get on to the work of learning how to find a derivative of a function, I'm going to share with you some important foundational knowledge that may make that task a little bit easier. One of the first things I'm going to share with you is rules of exponents. So we can do a variety of operations with exponents, of course. We can multiply exponents. So we could multiply x squared times x cubed. And you can see that they have the same base x, and each of them has a different exponent. One is 2 and one is 3. So when we're multiplying them together, as long as they have the same base, we can add the exponents together. 2 plus 3 equals 5, and that multiplication would result in a product of x to the 5th. If we look at a division of exponents, as long as they have the same base, we can simply subtract the exponent. So 5 minus 3 would equal 2. More likely you're going to see an exponent division looking like this, right? Looking like a fraction. Another way that exponents can interact with each other is, of course, having an exponent raised again to another power. And so here we have x squared raised to the power of 3. And in this case, we multiply those exponents together. And again, as long as the base is the same. So 2 times 3 is equal to 6. In some of our business applications that require finding a derivative, we may come across a square root. And we don't have a specific rule for finding a derivative of a square root, and so it's helpful to be able to convert that square root into an equivalent exponent. So in this case, the square root of x, it is equivalent to x to the 1/2. It's implied that there's a 2 there. It's a square root, but we don't write that. And so we may come across that same square root that's part of a fraction. So you might have something like 1 over the square root of x. And it is most helpful to write that in its equivalent exponent form, x to the negative 1/2. So here the 1/2 exponent represents that it's a square root. And in the second case, that negative 1/2, the negative makes a note that this was in the denominator, it's now in the numerator, and that just identifies it as that. So if I were to give you another example, if you had this cubed root of x, you can see the pattern here that the equivalent exponent would be, or power would be x to the 1/3. And again, if that were in the denominator, we could write that as x to the minus 1/3. So that's going to be helpful when we're finding derivatives when we have a square root or another root involved. We haven't done very much in this course around logarithms, but we will have done a little bit, and we will see them again when we're looking at calculus and taking derivatives. So it may help to have some basic understanding of how to work with logarithms. And primarily we've been working with ln, or the natural log, base e. And so they have some similar rules, just like we looked at the exponent rules. For example, if you have ln of 7a, for example, that is equivalent to ln 7 plus ln a. So you can see we can separate that ln function into two functions with an addition. And if we had ln of 7 over a, that could be written equivalently as ln 7 minus ln of a. We'll be looking at 8 different derivative rules. The top 4 here in the list, constant rule, power rule, exponential rule, and logarithmic rule, refer to terms that are standalone terms, terms that aren't in combination with other terms. The bottom 4, sum and difference rule, product rule, quotient rule, and chain rule, those are used when you have terms in combination with other terms. So sum and difference, for example, when terms are added or subtracted in one function. Product rule is when terms are multiplied together. A product, usually those are bracketed terms and they're multiplied together. Quotient rule, of course, quotient being a division, rational number, fraction. So there's a specific rule that applies to the terms that are interacting in that way. And chain rule. And chain rule is when you have a term embedded in another in a function. We'll look at some of those specifically. The first rule we're going to look at for taking derivatives is a constant rule. So a constant really is any term that's not associated with a variable. So it can be a number such as 7, could be a decimal, 0.27. It can be a fraction. It can be negative numbers, and so on. So the derivative of a constant is simply 0. The next derivative rule we're going to look at is the power rule. And when you start to apply derivative rules, really the most important thing is to be able to identify what type of term or function that you're dealing with. So a power is really a variable raised to the power of some exponent. So x squared, y cubed, and so on. So the general rule for taking a derivative of a power, where you have a variable raised to any power n, the derivative would be n times x raised to the power of n minus 1. So you're going to be subtracting 1 from the existing exponent. So let's look at some examples. So x cubed, the derivative here would be, well, n is 3, so we're bringing 3 down, x, and then n minus 1 will be 3 minus 1, or 2. So x cubed, the derivative is 3x squared. So what if we have a power like this? X to the 0.3. Does it still apply? Sure. So n here is 0.3, we bring that down, x, and then 0.3 minus 1 is going to be negative 0.7. So what if we have x to the 1/5? So we have a fraction exponent. N is 1/5, so we bring 1/5 down as the coefficient of this variable x. Then we have x, and then we subtract 1/5 minus 1. So we can write 1 or consider 1 as 5 over 5. So 1 over 5 minus 5 over 5 would be minus 4 over 5. But what if there's already a coefficient or a number in front of the variable term? Let's see, 3x squared. So here the derivative would still be nx to the n minus 1, but we have 3 here already. So we bring n2 down, and we subtract 2 minus 1, n minus 1, so that leaves 1. So we can put that there just to illustrate what we're looking at. And then we would simplify 6x. So the derivative of 3x squared would be 6x. So just one last example. What if we had 4x cubed? Again, we have already a coefficient in front of that x. We're bringing down the n. We have x, and then n minus 1, where n is 3. So our n minus 1, or our new exponent in the derivative, is squared. And we could simplify that. 12x squared would be the derivative of 4x cubed. So the next derivative rule we're going to look at is the exponential rule. So these terms or functions are the easiest to identify because they always involve e, or Euler's number, and the general derivative rule is any term e to the ax, the derivative is a e to the ax. So you can see that we're not subtracting 1 from the exponent as we did with the power rule. We're simply bringing that coefficient a of the exponent down in front and repeating that term again, e to the ax. Okay, so some examples: if we had e to the 2x, the derivative would be 2e to the 2x. It's one of the easiest derivative rules. But what if we had a coefficient already in front, just like we did with the power rule, right? We would multiply those together. To simplify, would be 6e to the 2x. The next derivative rule we would be looking at is logarithmic rules. We don't look at those functions very often, but you should still understand how to take the derivative. And again, in this course, we only look at natural log or ln. And so the derivative of ln x would be simply 1 over x. Those sum up the derivative rules when you have just an individual term, but terms can combine in a variety of ways, and so we need to look at how to handle those types of functions and find the derivative of those. So one of the ways that terms can combine is through sum and difference, meaning that you are adding so sum, and difference through subtraction. Okay, so let's look at an example. If we had 4x cubed plus 3x squared, and we've seen those individual terms before, minus 17. So the first thing you would look at is how they're combined. So they are indeed a sum and difference. There's no multiplication of terms, and there is no division, so no quotient rule needed. So we see that they are added or subtracted. And then the next thing you do is identify the rule that you're going to apply. Okay, so the first term, 4x cubed, is a power, so we would apply power rule. 3x squared is also a power, so we apply power rule. And then minus 17 is a constant, so we would apply constant rule. So the derivative here would be 12x squared plus 6x. Remember the power rule, x to the n, the derivative is nx to the n minus 1. And here the constant, the derivative of a constant is 0. Let's just try another one here. So what if we had a combination? We have an exponential term, we have a power term, and we have a constant. Highly unlikely you're going to see these in combination, so this is more of an example than anything. But again, you identify each term and apply the derivative rule that applies. So if we look at e to the 0.2x, we apply the exponential rule, so 0.2 e to the 0.2x. We look at the next term, x cubed, and we apply the power rule to that, 3x squared. And we go to the third term, negative 1.3, and we realize that's a constant, and the derivative of a constant is 0. The next combination derivative rule is the product rule. So a product is the result of a multiplication. So you could identify that you have a product in a function by looking at if there's a multiplication or not. I'm going to write the function in function notation. So if you have any function where you have something u, some terms u, multiplied by some terms v, the derivative would be the derivative of that first part multiplied by the second part plus the first part multiplied by the derivative of the second part. So it sounds complicated, but let's have a look at it and see how it goes. So we have this function, 3x squared plus 7 multiplied by 2x minus 5. Okay, so we would identify this as u and this as v. So the terms in the bracket as u and the other terms in the other bracket as v. My best advice is to make a legend to the side and identify each of the pieces that you'll need to apply the product rule. So in this case we have u as 3x squared plus 7, and u prime, which is how we say it, or the derivative of u, is 6x. We have v, which is all the stuff in the other bracket, and the derivative of v, or v prime, is simply 2. So now we have identified all the pieces we need in order to use this product rule. So the derivative of this function, which we identify by that little apostrophe, is equal to the derivative of the first, so 6x, times v, plus the first bracket, 3x squared plus 7, times the derivative of the second bracket. Okay? At this point, we have just a simple expansion to simplify and collecting like terms. So this would be 12x squared, if we expand it here, minus 30x plus 6x squared, because we're multiplying the 2 by 3x squared, and then the 2 by 7, so plus 14. So we can collect the like terms, the x squared terms. We will have 18x squared minus 30x plus 14. And that is the derivative of 3x squared plus 7, all multiplied by 2x minus 5. I did promise to give you some tips and tricks, and so here's one I'm going to just fit in here. So in the last example, we used a product rule in order to find the derivative of this function. But there's also an alternative, which will end up having you use the sum and difference rule. So you can actually just expand the brackets, and then you'll have a series of terms added or subtracted. And I like to use this little tool to just let me visualize what I'm multiplying, the term. So this allows me to multiply each term by each term, but not get lost and forget any. So 2x times 3x squared is going to be 6x cubed. 2x times 7 will be 14x. Minus 5 times 3x squared will be minus 15x squared. And minus 5 times 7 will be minus 35. Okay, so if I was to write this now as a complete function, I can't add any of the terms together because they're all unique, but we have 6x cubed minus 15x squared plus 14x minus 35. So I'm writing them in decreasing degrees, cubed, squared, x to the 1, and the constant. So now if I take the derivative of this function, I'm going to identify each term. They're just powers. I'm going to use the power rule. So in this first term, the derivative here is 18x squared minus 15x squared. The derivative is minus 30x. The derivative of plus 14x is plus 14. And the derivative of the constant minus 35 is 0. So here's the derivative. And you can see that we have arrived at the same derivative, of course, as when you apply the power or the product rule. The next derivative rule we're going to look at is the quotient rule. Quotients are, again, quite easy to identify and a bit more challenging to apply. So a quotient, you're going to find a function where you have some set of terms in the numerator and another set of terms in the denominator, so it will be u over v, and the derivative there would be u prime v, so the derivative of the top, the numerator, times the derivative times the bottom, minus the derivative of the bottom, the denominator, times the top, or the numerator, all over the denominator squared. So I'll use an example similar to the one that we use for the product rule. So 3x squared plus 7 over 2x minus 5. So we identify that as a quotient. And like I suggested before, it's really helpful and can prevent some careless errors if you just take parts of the function aside, find the derivative separately, and then you can substitute them in. So the top part, the 3x squared plus 7, is your u in this case. And the derivative of that u is 6x. The v is the denominator, and the derivative of that denominator, 2x minus 5, is 2. So now we're going to substitute them back into the derivative quotient rule. So u prime is 6x times v, which is 2x minus 5, minus v prime, which is 2, times 3x squared plus 7. So because we have a subtraction, we have to be very careful to make sure that we're using v prime u instead of reversing them. I see some common errors there in student work. With the product rule, it's an addition, so it doesn't cause as much, if any, problems, but here with it being a subtraction, you've got to be very careful that you're subtracting the v prime u. Okay, so that's all squared. So here you would just expand and collect like terms in the numerator. The denominator you would just leave as it is, 2x minus 5 all squared. So on the top here I would have 12x squared minus 30x minus 6x squared minus 14 all over 2x minus 5 all squared. So then I'm going to collect like terms that are in the numerator. So I have here 12x squared minus 6x squared, so they combine to leave us with 6x squared minus 30x minus 14, and again all over 2x minus 5 all squared. And that's your derivative. The last derivative rule we're going to look at is the chain rule. It's actually quite common, and what it refers to is really a function that is embedded within another function. So it would look like this, where you have a function and you have a g at x function internally. So the derivative of the big function multiplied by the derivative of the embedded function. So while they can look like they're a little bit complicated, if you just follow it step by step, it's actually quite simple. So for example, if we had a function like this, I'm going to recognize this 3x plus 7, all raised to the power of 4. So 3x plus 7, we've used those set of terms in a couple of examples now. So what if we suggested that this was u? We could pull that aside, 3x squared plus 7, and the derivative would be 6x. Okay? So the chain rule says that we take the derivative of the big function. So the derivative of that big function, which is this entire thing, would be 4 times whatever's in the bracket raised to the power of 3, right? Because this is technically like something to the power of 4, and we were really applying the power rule. So n and then n minus 1. That's the derivative of the big function. And then you have to multiply by the derivative of what's in the bracket, or the embedded function, which we've determined is 6x. Okay? So here it's just a matter of simplifying. We would multiply 4 by 6x, which would give us 24x, times 3x squared plus 7, all raised to the power of 3. And that would be your derivative of that chain function. So that wraps up the Calculus Bootcamp, the online summary. We covered a few things. What is a derivative? Basically the math term, and then how do we see derivatives in our business applications. We looked at some foundational skills that will help us to apply derivative rules more easily, so rules of exponents, logarithms, roots. We looked at some key words that we're going to see in our business application questions. Then we looked at the derivative rules, specifically constant rule, power rule, exponential rule, logarithmic rule, and then those combination rules, sum and difference, product, quotient, and chain. And I added a couple of tips and tricks along the way. I hope this has been useful.